This video is an experiment where I answer viewers' questions, mostly mathematical questions. First question says, what are the important criteria for choosing a problem? What are some areas that I think deserve more attention? And what would I really like to understand? Well, the most important criterion for choosing a problem is it has to be something you're really interested in, because if you're not really interested in something, you're not going to be successful at doing research on it. Another criterion is that it should be something few other people are doing, because there's few things worse than working 5 years on a problem and being beaten to it by a week by somebody else. As for what deserves more attention, my guess would be most top math departments are not paying a whole lot of attention to computer proofs in mathematics, and my suspicion is that in 10 or 20 years these might have got good enough to be a serious rival to mathematicians. For what area I'd like to know more about, I guess Langland's programme. Who is the nicest or kindest mathematician I've ever met? Well, most of the mathematicians I've met are fairly nice. In fact, it's hard to think of any counterexamples. If you want a particular example of someone who was particularly nice to me, my supervisor, John Conway, once sort of more or less rescued me. When I was just starting off as a graduate student and floundering a bit, he heard about this and went out of his way to meet me and offer me a position to work with him. And I noticed that he actually did this with several other people, so he actually had a habit of helping out graduate students in trouble. Next question is, are classic mathematics texts such as the one by Gauss worth reading? Well, classic mathematics texts have the big advantage that if you read the original account of some subject, it's usually much easier to figure out what the key ideas in it are. You can see the person kind of struggling a little bit trying to figure out what's going on. Whereas if you look at something later, everything is very slick, but the original key ideas are often buried under a mass of generalizations and axiomatization and so on. In particular, Gauss's book on number theory is still well worth reading, and what is rather striking about it is the huge amount of numerical calculation Gauss does. Pretty much every page of this book has some sort of calculation, whereas if you look at a modern book on number theory, it tends to be an awful lot of theorems and proofs, but not so much actual calculation. So, next question is, what theorems were influential, and would I recommend theorems for aspiring mathematicians? Well, one theorem that was particularly influential to me was Dirichlet's theorem on primes in arithmetic progression. I remember when I read this, I was really amazed at how you managed to prove something about primes by using analysis. Would I recommend theorems? Well, I'm not so sure. I mean, if you mean memorizing proofs of theorems as some undergraduate courses expect people to do, I think that's largely a waste of time, and time would be better spent in calculating with examples to try and understand what's going on. Next question is, what are my thoughts about the monster group and the classification of finite simple groups? Well, I find the monster group completely bizarre, and the classification even more so, because the problem is this: when you take the axioms for a group, they're really simple and natural. You can write them out in one line, and somehow hidden in that one very simple line are all these bizarre things like all the sporadic groups and all the monster group. The trouble is explaining why the monster group exists is probably one of these questions like, why does the universe exist? Which I not only don't know how to answer, I can't even imagine what an answer would look like. So the next question is, what do I think mathematics will look like in about 20 years from now? Well, as I said, I think one of the main changes over the next few decades in mathematics is we're going to switch to a model where all theorems have to be formalized and verified by computer. At the moment, we can't really do this because turning a proof into something a computer can check is just too painful most of the time, but the computers are getting better and better at doing this, so my guess is we'll soon be switching to that model. So what is my favourite mathematical proof? Well, I could recycle a previous answer and say the proof of Dirichlet's theorem is also very nice. Another one I really like is one of Gauss's proofs of the law of quadratic reciprocity using Gaussian sums. So what mathematical targets do I hope will be hit in the next few years? like most mathematicians, any famous mathematical question that's proved would be absolutely great. You know, Riemann hypothesis or P not equal NP or whatever. I don't have any idea which one is likely to be proved next. So next question is, what postgraduate topics would I recommend for someone to learn for pleasure? Well, this is kind of like somebody asking me who they should date or marry. It really depends very much on your own personal preference. But if I have to suggest one particular topic, I would just suggest modular forms as being the most magical of all mathematical topics. So what is the most interesting mathematical problem I've worked on? Well, I guess that would be the moonshine conjecture that relied on this bizarre observation of John Mackay that one of the coefficients of the elliptic modular function was more or less one of the dimensions of the monster simple group. And that was really bizarre because there was no obvious connection between these two fields at all. Okay, the next question is, can computers produce valid proofs, and what will the foundations of mathematics be in the future? Well, as one of the answers to that question said, computers are already producing valid proofs in certain rather restricted areas. There's some, I think one of the most famous examples of this is the proof of the four-colour theorem, and I expect computers will gradually infiltrate more and more mathematics. As to what the foundations of mathematics will be, well, the foundation of mathematics have never been set theory or category theory or type theory, never will be. The foundations always consist of properties of the natural numbers. Now, set theory is a very useful and powerful method of describing properties, very complicated properties of natural numbers, and category theory and type theory are wonderful bookkeeping devices for doing mathematics, but none of them are truly the foundations of mathematics. They're all sort of, they're not really fundamental. The next question asks several questions about this channel, such as how did I start it and what does my department think of it? I started it because, almost by accident, that I had to give some algebraic geometry lectures, and I put them on YouTube because the university's video system wasn't really all that good at the time. What does the department or university think of it? I haven't asked, on the grounds that it's easier to ask for forgiveness than for permission. Exercises in my videos, this is a very good idea that I keep meaning to put more of them in it, but I'm just kind of always too lazy to do so. How do I write the scripts? Well, honestly, I don't really write scripts. For my videos, I sketch some rough notes and write out any complicated formulas or calculations that I need and kind of wing it, which is why my videos have so many errors in them. Next question is, which fields that don't directly use mathematics but benefit from it? Well, this is a bit of a tricky question because the fields that benefit from mathematics are almost always ones that use it directly. I guess you could argue that maybe something that uses logical reasoning but not mathematics like law might benefit a little bit from it, and there was certainly at least one very famous mathematician, Cayley, who was a lawyer. The next question is, how do I deal with setbacks? And was I always good at everything? And how do I go about learning new mathematics? Well, setbacks and difficulties, my normal procedure for dealing with difficulties is to ignore them, because it's amazing how many problems go away if you just do nothing about them for a while. How do I learn new mathematics? Well, it's kind of rather difficult. In order to learn new mathematics, I generally have to reread something 10 or 15 times and do lots of working with examples and so on. I certainly don't find it easy learning new mathematics. In fact, I always find it surprising that humans can do mathematics at all. I mean, our brains were adapted for running away from saber-toothed tigers and things like that, and anyone who was good at mathematics would have been eaten by a tiger while contemplating some mathematical fact. So why we've still got the genes for mathematics, I don't know. So the next question asks for me to comment on the relation between representation theory and geometry. Well, geometry is one of the best ways of producing representations of groups. So what you do is you start with a group acting on some geometric object. For instance, you might take the orthogonal group acting on a sphere. And then you can construct lots of representations just by looking at, say, the space of functions on the group, and that gives the space of functions on the sphere, and that gives you a representation of the group. More generally, there's a very powerful method where instead of taking spaces of functions, you take various sorts of cohomology groups of the space the group is acting on, and this is about the most powerful method we have for constructing representations. What is my favourite movie? Oh, well, this is a tough one. I guess I should actually give you a movie. How about Whiskey Galore, the original one, not the recent remake. Next we have, do I have any advice for young mathematicians? Well, one general piece of advice is if some piece of mathematics you're studying isn't fun, then stop studying it and work on something else instead. Actually, that's pretty good advice for life, not just mathematics. Next question, will I be going deeper in my complex analysis course? The answer is probably yes, but it sort of depends on what I feel like and what happens with COVID and so on. Next, which millennium problem do I think is most likely to be solved next, and which one would I care most about and why? Well, I think the one that's most likely to be solved next is probably the Birch-Swinnerton-Dyer conjecture, because most of it has already been done. I mean, in some sense, Andrew Wiles proved the biggest part of it about 20 or so years ago by showing that most elliptic curves are modular, and we sort of got a pretty good understanding of the rank 0 and 1 case, and my impression is it only takes maybe one more good idea to fix it. Which one would I most like to see solved? The Riemann hypothesis. Why? Because it's the Riemann hypothesis. Next question. Apparently I know how to do quantum electrodynamics rigorously. Can I discuss my ideas? Well, that's easy to answer. I don't know how to do four-dimensional quantum electrodynamics rigorously, and have a strong suspicion as it might not even exist as a rigorous mathematical topic. I was thinking some time ago about trying to understand Feynman integrals, and the main idea I had about these is that if you're trying to integrate over an infinite dimensional space, there's a huge family of translation invariant integrals, an infinite dimensional space of them, which are acted on transitively by an infinite dimensional group. And this may account for why integrals over infinite dimensional space are so difficult, but I never really managed to understand that well enough to understand quantum field theory. Next question, what do I think about Jacob Lurie's work on infinity categories, and is quantum field theory related to the Langlands program? Well, that's easy. What I think about Lurie's work on infinity categories is it absolutely terrifies me. There's a couple of thousand pages he's written about them, which I made a start on trying to read, and I must admit I got kind of lost in it. Is the Langlands program related to quantum field theory? Well, it wouldn't surprise me at all if it is, although I haven't been paying close enough attention to it recently to know for sure. Next question, does math have any purpose about or say anything about philosophical and non-mathematical concepts? I think mathematics is really good at saying things about the physical world, and the fact that it's really good at this is extremely mysterious. I mean, for instance, much of physics depends on mathematics, and in some sense we don't really know why. As for whether it is anything more than scribbles on a piece of paper, well, Maxwell's equations were just mathematical scribbles on a piece of paper, but underlie most of 20th century technology. Next, how do I take notes while reading math-related books? Well, that's easy. I'm much too lazy to take notes while reading a math book, which is probably why I have difficulty remembering the stuff I've read. Next question, what is a theorem I like very much? Well, I've already given a couple of examples of this, Dirichlet's theorem and one of Gauss's proofs, so I guess I'd better come up with another example of this question. And I'll just mention that Deligne's first proof of the Weil conjectures has always kind of fascinated me, although I've never really managed to fully understand the proof. So next question, what do I think about Peter Schultz's work? Well, it's on my long list of things I really wish I had time to understand. As Tim Gowers said, there are too many things to learn and not enough time to learn them in. So is there a proof that I think is worthy of the book, and how do I go about learning a new topic? Well, the book they're referring to, it may be this one here, which is proof from the book, and this is the idea that for every mathematical theorem there should be a unique best possible proof. I don't really have any proofs for this book, and I don't really agree with this idea that mathematical theorems have best proofs. Generally, mathematical theorems have several different proofs which give you different insights into it. As for how I learn a new topic, with great difficulty. The main thing to do is to find what are the key examples in the area and study those in great detail. For example, if you were doing, say, representation theory, the key example is the group SL2 of R, so you should study representations of SL2 of R in great detail in order to learn representation theory. So what's the most efficient way to study math at university? Well, again, this is one of the things which varies a lot from person to person, but some general things I would suggest. First of all, you don't waste time trying to study topics you find boring. Secondly, don't waste time memorizing proofs. Your time is much better spent in doing lots of calculations and looking at examples. So is a noncommutative polynomial ring over a Noetherian ring also Noetherian? Well, this actually depends on what you mean by polynomial ring. I think if you're talking about the free polynomial ring, it's generally not Noetherian. If you're talking about a skew polynomial ring, it generally is Noetherian. If you want to find out more about this, there's a very nice book on non-commutative Noetherian rings here by McConnell and Robson, which will answer most of these questions. So what sources can I recommend for mathematical quantum field theory? Well, there's two volumes called Quantum Fields and Strings, a course for mathematicians. The only problem is they're two very, very fat volumes, so you'd better have a lot of spare time on your hands. So why did I decide to be a mathematician? I didn't decide to be a mathematician any more than a dolphin decides to be a dolphin. So the next question is, why was John Conway not very happy with my proof of monstrous moonshine, and do I have any anecdotes about Simon Norton? I'm not quite sure what Conway's opinion was. I think Conway, the problem with monstrous moonshine is that the monstrous moonshine conjectures talked about genus zero modular functions, and if you've got a genus zero object, you should actually have a sphere in there somewhere. And my work, there weren't any obvious spheres, and this may have been one of the reasons why Conway was not entirely satisfied by it. It didn't really explain the genus zero property. If you want a story about Simon Norton, I was once discussing some rather technical problem about finite fields with Richard Taylor, and we had both been thinking about it for 10 or 15 minutes and were kind of baffled. And Simon Norton was walking by, and so I asked him as he passed, and he just answered it like that without breaking step and carried on walking out of the room. He was frighteningly fast at those sorts of questions. So what are my favourite books or papers? Well, again, I don't have any particular favourites, but papers by Serre or books by Serre are always really great to read, because he's not only a fantastic mathematician, but he's also really great at exposition. If you want some specific book as a recommendation that I particularly like, I'd say the book Number Theory by Borevich and Shafarevich. So what's my forecast for the future of academic positions in mathematics? Well, I've been kind of wondering about this, because in the first place, as I mentioned earlier, computers in a few decades may be better than pure mathematicians at research. And as for teaching, well, I'm kind of wondering if my YouTube lectures are going to end up putting me out of a job, because now that I've made YouTube lectures on all these courses, why does the university need me anymore? So what do I wish I'd known when I was younger? Well, I guess I wish I'd known to buy Bitcoin 10 years ago. So will I go through my original notes outlining my process of discovery with some of my work? Well, I did actually make a couple of videos saying a little bit about this, but it's actually a little bit stressful talking about my own work, which is most of my videos aren't on my work, so possible but not very likely. So how to find problems without the help of a teacher? A bit tricky to answer this because I'm not quite sure what level of problem. If you're talking about problems at an undergraduate or high school level, then a good way is to go to the library and browse around until you find a textbook that you think looks interesting and look at the problems there. If you're talking about a research level, it's very difficult finding a good research problem without someone's advice. There are problem lists, like for example Kirby's problem list in geometric topology, but it's very hard to tell which problems are good ones to attack or which ones are just hopelessly difficult. So next question is, what is it like inside your head? Well, I guess literally it's kind of squishy. If you mean how do I think, I don't really know. It's very hard to tell. This is a notorious problem in artificial intelligence, that if you've got a neural net solving a problem, it's incredibly difficult to understand how the neural net is solving the problem. The mathematician Jacques Hadamard actually asked a very similar question to a lot of mathematicians about a century ago. So if you really want to know, you could try looking up what conclusions he came to. So what's the motivation for stacks in algebraic geometry? Well, the person who asked this question gave a very good answer to it. The motivation was to define moduli spaces. Slightly more precisely, they were introduced to define moduli spaces for objects that might have automorphisms. Next question, how do you find out which math departments are good when you're applying there? Easy, you ask the grad students. They're the ones who know everything that's going on. I used to know everything that's going on until I stopped being a graduate student, and when I was out of the grad student grapevine, I no longer knew what was going on. So do I still do research, and if so, what on? Yes, I'm still doing research on a rather difficult problem, and I'm not going to tell you what it is because, as Mark Twain is supposed to have said, it's better to remain silent and be thought a fool than to open your mouth and remove all doubt. Next question is, what's so special about 8 dimensions? Why does it crop up so much, as in the E8 lattice and Bott periodicity and so on? The answer is I don't know. It has actually baffled me a bit, and I've never come up with a good reason for this. The only thing I can say is that everything that happens in 8 dimensions also has a sort of echo in 24 dimensions. So there are large numbers of equally weird things going on in 24 dimensions. For example, in 8 dimensions you get the E8 lattice. In 24 dimensions you get the Leech lattice, which is very similar. So this is one of these big mysteries, like why does the monster exist, or why does the universe exist? So what are the deepest theorems I know that I'm baffled by? Well, there are just too many deep theorems that I'm baffled by. I guess I better just give one example, so I'll just say the classification of finite simple groups. This completely baffles me because the starting point is so simple. You're just asking for the finite groups, and you can ask that question about a line, and the complete classification takes 20,000 pages and is incredibly complicated and difficult, and there's no way I'm ever going to understand it. So what do I think of YouTube and the other math and educational channels on it? Well, YouTube is kind of interesting. Most of the other educational channels I've seen on it look great, except they kind of make me feel a bit embarrassed because they all put so much more effort into presentation. They have nice graphics and animation, and I'm just sort of doing something very simple. So, can I give an interesting story? Well, this is a kind of open-ended question. I guess one that John Conway once told me was that there was a book on logic written by a sort of amateur mathematician, and Conway mentioned to Martin Gardner that the book was essentially content-free, and Martin Gardner published this in his mathematical games column. The author of the book then attempted to sue Conway for slandering him, and this was Ian Cassels, who was chair of the department at the time, managed to put a stop to this by pointing out to the author of the book that he had an overdue library book from the math department library, and by an odd coincidence, the fine for this overdue book was exactly equal to what he was suing John Conway for. So how am I? Well, I'm surviving, which is pretty much all I ask for these days. So here are two questions. Is there a result I'd like to see proven? And what does the Langlands program have to do with representations of finite groups? Well, the obvious default answer to what I'd like to see proven is the Riemann hypothesis. As for what the Langlands program has to do with representations of finite groups, George Lustig's classification of the representations of finite groups is more or less the analogue of the Langlands program for finite groups. So yes, there is a very deep connection between them. So can I talk about Neverlina theory? Well, very briefly, Neverlina theory is a theory about meromorphic functions, which says, roughly speaking, that most meromorphic functions take every value the number of times you would expect, with a very small number of exceptions. So the next question is, roughly, how do you deal with being depressed while struggling to do research? Well, this is actually a really common problem for mathematicians. I remember once looking at a poster saying, recognise the following signs of depression, and I looked at this and I thought, well, that sounds to me like the normal state of a graduate student, judging from the time I was a graduate student. So as the person asking the question says, an awful lot of people suffer from this problem because research in mathematics, a lot of the time it consists of struggling very hard and making no progress for months. What can you do to deal with this? Well, one thing is to find something else to do. Richard Feynman, for example, recommended teaching, so at least you're always doing something. John Conway once mentioned to me that one of the things that he did was he always had a sort of background project, which was just computing a lot of things like maybe group representations or knot invariants. So whenever his research was stuck, he could go and do a bit more calculation. If you're really desperate, you could always do something like start a YouTube channel on mathematical topics. So who should have got Fields medals and didn't? Well, in order to avoid upsetting people too much, I'm just going to confine myself to mentioning a few people who are no longer alive, and some names that are often sort of talked about are people like Andre Weil or Hirzebruch or Harish Chandra, and there are various rumours floating around that most of these people didn't get their Fields Medal for various political reasons, that there were certain influential mathematicians who either disliked them or were promoting their own area or something. So there's a lot of politics and luck involved in who gets them. So how does mathematics influence my view of things around me? Well, it makes car number plates a lot more interesting because you can practice factorising them. So next question is, what is my best algorithm for computing specific things? Problem is, the answer to this is a bit technical. I did actually have an algorithm for computing lattices in 25 dimensions by just sort of drawing little doodles on a piece of paper, but can't really explain that in 30 seconds. So what are my mathematical weaknesses and which areas do I find hard to comprehend? Well, I guess one of my mathematical weaknesses is I'm rather bad at networking with other mathematicians, and most of the top mathematicians tend to collaborate a lot more than I do. And which areas do I find hard? Well, I find most areas of mathematics pretty hard, but I had a particularly bad experience with trying to understand infinity categories. So what areas would I like to know more about, and what am I currently working on? Well, I'd like to know more about most areas of mathematics, but there's really beginning to realise there's rather a shortage of time. If I have to name a particular area I'd really like to understand, it's the Langlands program. As I said in an earlier question, I keep quiet about what I'm actually working on unless it actually works. So what is my favourite mathematics book? Well, I don't really have a single favourite math book, but I'll just mention one, the book A Course in Arithmetic by Serre. The title is a mistranslation from the French, by the way. It should really have been called A Course in Number Theory, because arithmetic in French tends to mean number theory. So am I planning to make a course on Jacobson theory or Hopf algebras and Galois theory? I wasn't really planning to. My suspicion is that the whole concept of Galois theory for inseparable extensions should be done not using Lie algebras, which Jacobson did, but using algebraic group schemes. However, I haven't managed to find a good book or paper explaining this. So, do I see a future for string theory? Well, that's a rather controversial topic in physics, and I was actually thinking of making an entire video about it. In mathematics, there's certainly a future of string theory. String theory has produced a lot of very good mathematical ideas, and even if physicists eventually abandon string theory, mathematicians will still be doing it. So what's my favourite book in literature? I guess the one I've read most often is probably The Lord of the Rings. So what is my favourite number and why? Well, I've got several of them listed on my YouTube channel main page, which you can see here. What is special about these numbers you have to figure out for yourselves. Next question is applications of algebraic geometry and algebraic topology to computation. I think I'm going to have to sort of pass on this. It sounds like a very interesting idea, but I simply don't know enough about computation to say anything very useful. I think Gunnar Carlson had some applications of algebraic topology to various sorts of computation with large data sets, so you could look into his work. So what's my favourite area of mathematics? That's easy, it's modular forms and related things like algebraic number theory. So how did I study mathematics as an undergraduate? Well, not very efficiently. When I was reading books, I didn't bother taking notes. I didn't bother reading books systematically, so I just skip over all the boring parts and only bother reading the bits I was interested in. And I'd often skip proofs of theorems because it's not terribly interesting reading proofs of most theorems. And what I would do more is try and calculate examples to try and figure out what's going on. So have I thought of making videos of first and second year lectures? Well, I sort of briefly considered it, but there seem to be plenty of such lectures on the internet at the moment, so there's no great priority for them, so I probably won't be doing them in the near future. So next question, is it too late to start doing mathematics at 24? Not at all. It's quite rare for people to start doing mathematics that late, but some outstandingly good mathematicians started doing mathematics surprisingly late. For example, I think Ed Witten, I believe, when he was an undergraduate, he was studying history and didn't start taking mathematics seriously until he was about 22 or something. And he's now one of the world's best mathematicians. So if you're interested in mathematics, then go for it. So is it possible to do mathematics outside academia? Well, it certainly is. In fact, many of the famous mathematicians from the past were not working in academia at all. I mean, people like Fermat and Cayley, for example, were both doing law. It's become much rarer these days for people outside academia to do mathematics. I think that may be because it's much easier for someone who's really interested in mathematics to get a job in academia than it used to be. So it's certainly possible, but a bit rare these days. So what about Mochizukis' proof of the ABC conjecture? I just don't know. I'm not qualified to have an opinion about Mochizukis' proof on the ABC conjecture, and there are only about maybe half a dozen people in the world who are. This is an incredibly difficult proof. I tried reading it and just gave up after a few hours. It was obviously going to take me years of work to even begin to understand what's going on in it. The problem is we have this very unusual position in mathematics that the small number of experts who understand are disagreeing with each other about whether or not it's correct. So there are 2 or 3 people whose opinion I respect who say it's correct, and 2 or 3 people whose opinion I respect who say it's not, and quite a lot of people whose opinion I respect who say they just don't know. So I have no idea what's going to happen. The problem about whether the proof is correct will probably be resolved in a few decades at latest, because, as I said, I think we're going to switch to all published mathematics being verified by computer, but that's not going to happen in the near future. So maybe in 20 or 30 years, the computers might be good enough to resolve this question. So next, can I explain the most general interpretation of the derivative in less than 2 minutes? Yes, a derivative simply describes the first order linear approximation to a function. So any interesting or funny stories about John Conway? Well, I can tell you about a story John Conway told me about his water-powered computer. I'm not entirely sure whether this story is actually correct or not, but who cares? So John Conway noticed that if you look at a urinal or in a public restroom, it has a sort of interesting switch property that if you fill it up with water, it does nothing until the water reaches a certain level, and then it suddenly sort of switches into a different state. So he claims he once built a sort of smallish computer on this principle and even exhibited it somewhere. The big problem was when you tried doing arithmetic with it, it used to have overflow errors. Okay, well, I guess that's all for the questions this time. I might do another question session later, so if you've missed this one, just look out for the next one.